Hi everyone, welcome to today's session. So today at Gboard we'll be solving another problem solving exercise, which is basically DSA, data structure algorithms, and trying to find out the most optimized way for solving commonly asked DSA interview questions. So before I begin, uh, like if you would like to subscribe, please do subscribe the channel for getting all the updates. And for any additional business inquiries, please feel free to reach out to our website, gboard.com. And for contacting us, these are respectively the numbers, the US, Canada numbers, as well as the Indian numbers. And this is the website. Cool. So let's get started. What problem we'll be solving? This is the problem sliding window and the max sum problem. So what the problem is and how to go about it, let's quickly discuss. So sliding window is basically a pattern that we can use, or you can also say an algorithm that we can use, and that applies to a wide variety of problems. So the benefit of understanding common patterns, common algorithms, is that we can repeatedly apply the same pattern, the same algorithm to a wide variety of problems. So this pattern we are going to apply over a question which is very commonly asked in interview, especially DSA interviews, maximum problem. So what is the maximum problem? So let me quickly type it out. We are given an array. Let's call it nums, and it can have, it need not be sorted. Right. So let's imagine this is how we declare an array. We have something like this, and it has any random numbers. It need not be sorted. Right. Something like this. So now we are given this array. We are also given a window size. Let's say the window size is 3, it can be anything. So we are given these two inputs, the integer array, which need not be sorted, and a window size 3. And what do we need to find? We need to find the maximum sum for this window size, the maximum sum for this window size. So before going deep into the discussion, we should quickly understand the difference between substring and subsequence. So here we are talking about the max sum. So we're talking about basically the subarray, the max sum subarray problem. The difference between a subsequence and a subarray is, in subarray, the window size is 3, so I have to count 3 items. However, there should not be any differences in the index. Let's quickly draw this out, and then it will become all the clear. So let's say this is an array. It is having these indices. Array indices always starts from 0. So if I am intending to find 3 consecutive items, and I'm talking about subarray or substring, in that case, the 3 consecutive items can be these 3, right? 0, 1, 2 are consecutive, or it can be these 3, or it can be these 3, right? So the consecutive items can be 0, 1, 2, it can be 1, 2, 3, it can be 2, 3, 4. It can also be 1, 2, 3. It can, yeah. So these are the different items, the consecutive items of window size 3 that is possible. That is what subarray or substring means. The difference between subarray and subsequence. So this is about subarray or substring. In subsequence, it includes whatever the subarray or substring has, right? So all these possibilities, 0, 1, 2, 1, 2, 3, 2, 3, 4 is possible with the subsequence as well. Plus, it can also include combinations where we are missing an index. These need not be consecutive. So what I mean, you can have 0, 1, and 3, right? 2 is missing. The index 2 is missing. That's perfectly possible. 0, 2, and 4. Something is missing here, something is missing here, but we have 3 items. That is also possible. So if missing indices are allowed, That is what subsequence is. However, in subarray or substring, it has to be consecutive. We cannot have a missing index. So that is the difference. In this question, it's talking about a subarray. So we have to keep everything gelled together consecutively. No indices should be missing. So now in this context, I have, let's say, the same data, 10, 0, minus 1, 20, 56 need not be sorted. And I am having these indices. So 3 consecutive indices, right? These are all the possibilities I have, 0, 1, 2, 1, 2, 3, 2, 3, 4. I cannot have 3, 4 because after 3, 4, there is nothing. And my window size has to be 3. So out of these 3 possibilities, what is the sum of the value stored at these indices? So ARR of 0 is 10, ARR of 1 is 0, ARR of 2 is minus 1. So if you add them up, it will be what? 9. Similarly, for these indices 1, 2, 3, so you're basically talking about ARR of 1, which is 0, ARR of 2 is minus 1, and ARR of 3 is 20. So again, the sum will be 19. For 2, 3, 4, we're basically talking about minus 1 plus 20 plus 56, 75. Right. So in this case, it is very clear that the maximum sum is 75. You have to compare this 9, 19, and after comparing these 3, what is the max? That is the question. And the answer is 75. So that should be the answer. We are basically getting the maximum possible sum by adding n elements. N is the window size. And this has to be a subarray, that is consecutively. So consecutively 3 elements has to be found such that adding all those 3 elements, the sum becomes maximum out of all such possible combinations. So these are the possible combinations out of all, and for all these possible window size 3 subarrays, the sum of these subarrays are 9, 19, and 75, and out of them, the max is 75. So the answer is 75. This is the question, and how do we approach this question? So one can be the brute force approach. Brute force approach. So the brute force approach, what you can do is, let me quickly redraw it real quick. Right, the window size is 3 in this case, as an example to understand the flow. So you can add these 3 elements, right? You can add these 3 elements. You can add these 3 elements. So what you can do, you can start a counter or a loop. You can start from here and add the 3 elements. This will be the addition, right? You will get some value. In this case, you will get 10 plus 0 minus 1, which is 9. And then you can move your counter not to here, but start from here, and then again start counting 3 elements. So in this case, will be 0, minus 1, and 20, 19 in this case. And you can keep track of these individual sums. And then again, you can move your counter and start counting from here. And in this case, you will have something like this. You will get the third individual sum is 75. And then if you move the counter, you cannot move the counter here because there is nothing at this position. You're basically at the end of the array. So you can start a for loop and then you're counting something like that. So you can basically run a for loop. I is equal to 0 to what index? In this case, I'm stopping it here, right? 2. So how do I get 2? Basically, I got 2 by the length. What is the length? Length is 5. And 5 minus 3 is how I've got the answer 2. We have to move from 0 to n, where n is 2 in this case. And in generalized form, how do I get 2? So basically, length minus window size, WS. So this way you can calculate n, and this way you can increment the counters. And then you can have a second loop. and this will be 3 times, right? The window size is 3. So that way you can get this element, this element, this element, sum them up, you get the sum. And then the next increment of the outer for loop, I will become 1. So initially started with 0, then I will become 1. So you will be starting at this. And then again, the loop will run 3 times. So you will get 0, minus 120, 90. And then again, in the next increment of the outer for loop, you will be basically starting at this point. And then again, the inner for loop will run 3 times. So you will add minus 120 and 56, minus 120 and 56, adding them up, you will get 75. And then you can write some variables to keep track of these individual sums. And towards the end, you can get the max sum. This is the brute force approach, which is not so efficient solution, but that's okay. In an interview, it shows that you have not memorized anything, because brute force comes intuitively. You're not rehearsing something that you've already seen. So that's a good way. But if you analyze the complexity, it is very close to n square, right? 2 nested for loops. So anytime you have this nested for loops, usually the runtime complexity is high and we have to minimize it. So in such questions, we have to use the sliding window algorithm. What is sliding window and what is the benefit? Let's quickly understand it. So what we are doing, let's have a long set of some numbers. And let me put any random values. Right, random values. And again, the window size WS, let's say it is 3. So according to this logic, let's keep the window size a little bit longer. Instead of 3, it is, let's say, 7. And let's have a really long initial subarray or subsize, that is nums, right? Let's call it nums. This is the original array. For this, we have to get all the subarrays of size 7. Window size is 7. So all the subarrays of window size 7, or all the subarrays of size 7. Among all those possible subarrays, get the count, individual count of each of the subarrays. And among those individual counts, what is the maximum? That is the answer to this question. So again, by the brute force approach, let me change the marker. If you go by that brute force approach, you will basically sum these things, right? 5 and 6. This is the sum you will get as the sum of the first possible subarray. And the next time you want this sum, right? So in the previous, this kind of approach, once you get this sum, you're adding all these items one by one, you will get the, let's call it subarray 1, you got by adding all these items. So that is nums of 0 plus nums of 1 plus nums of 2, and so on till nums of 6. This is how you got, and that's the first subarray. Now you're trying to keep track or get the value of the second subarray, and the second subarray's individual sum will be got, right? We're talking about index, so from nums 1 onwards. So nums 1, nums 2, nums 3, and so on and so forth. This is 7, right? So till nums 7. And similarly, you will write all other possible subarrays. And then you are going to basically, this expression will have some value. This whole expression, the addition of all the elements, will give you the individual sums, and you will compare all the individual sums to get the max, which is the maximum of the individual sums. So now in this question, if you go by the traditional brute force approach, if you examine these two things, just examine these two things, and you will get some hint where we are going. So everything else is the same. This part, nums1 plus nums2 till num6, right? This part is basically same as num3 for this, and you will have 6 here, right? Just before 7, nums of 6. This is the same. But what we are doing, what is bringing inefficiency in the brute force approach, even for getting the subarray 2, we are basically doing this repeatedly. So if we have got this as a result of a previous calculation, while calculating subarray 1, if I have this whole value, right, why not use this value here? Because we don't, then if we have this pre-calculated value, we can use it here. And then we are not intending to do this calculation repeatedly. Similarly, whatever subarray we have got as subarray 2, for subarray 3, the pre-calculated, pre-computed value as a part of calculation of subarray 2 can be used. So this is what is going to bring efficiency here. We are going to use the calculations done in the previous iteration. So for calculating subarray 2, we are going to use the calculations done in previous iteration, subarray 1. We have this value, right? And this value is supplanted here. So if I call this sum 1, and if I call this sum 2 S2, so S2 can be achieved how? Basically, if you examine this, S2 is same as S1 with some difference, and the difference is, like, these are same, but in S2, I'm adding something and removing something. What I'm adding is basically the next element in the chain. For X1, the last element was 6, right? So the next element, next index is 7, nums of 7. This is what I'm adding here. And also from the previous backend side, I am reducing someone. So in this case, I am reducing basically nums of 0. So I have to write this side, but I think we can get the flow. We have to reduce nums of 0. So this from S1, if I get rid of this, right? If I get rid of this, and I have everything like this point copied as it is, like this, and this additional thing I've added here, nums of 7. So then I am able to get S2. So now look at this. We are not needing to do all this computation for S1, right? S1 computation was not needed. And this saves a lot of time. Imagine this is just talking about 1 to 6. How many 6 elements? If this was an array of 1,000 elements and the window size was 100, approximately 100 computations we have saved. If we are following the new approach, and this is what we are going to do in the new approach. In the brute force approach, we are not going to like redo this operation. We are not going to redo this operation. We are going to use it. And in terms of programmatically, how do we achieve it? Let's get to that point as well. Let's make clear everything. And let's have any simple subarray or subsize. Let's keep it random. Cool. So programmatically, if you understand the flow, what we are doing, then it's pretty simple. So we are going to maintain 2 sums. One is the max sum, and we are going to initialize it with 0, and we are also going to maintain something called the running sum. This will be the individual sums. We'll talk about it. Let's try to code it out. So how, like, you don't need to memorize anything. After seeing this video, it might take some time to sink in the concept, but once the concept and the pattern, the sliding window pattern has synced into you, after, let's say, 4 months, 5 months, if you want to have a recall, this should come intuitively to you. So what we are doing here, no need of like memorization, anything. We're basically traversing the whole array. That is how we are going to do it. But we are only traversing it once. In the brute force approach, we had 2 nested for loops, right? We were traversing first the external loop using external for loop, and then inside the external for loop, I'm running another inner for loop that was running from 0 to window size. And so in this case, let's keep the window size as 3 again. Right. So in the brute force approach, I was running 2 for loops, index 0 to n minus 1, basically the whole array. And then inside that, I was running another for loop 3 times, right? So you can say 0 to 2. This 3 times is, how do I get this 3 times? This is basically n minus 1 or window size minus 1. So 3 minus 1 in this case, that is 2. And then I was doing the calculations. So this is how what was spoiling the efficiency of the program. We still need the external for loop because we have to traverse at least once. Only then, if we don't traverse, we won't be able to read what is there at these indices position. So at least once we have to travel. Now we are moving slowly from the brute force approach to the optimized approach. Right, we are moving from brute force approach to optimized approach. So one for loop definitely we require. So I'm going to run it from I is equal to, and this is going to examine each and every element or value. So 0 to n minus 1, n is the length of this array, which is in this case, it has 6 elements, right? 1, 2, 3, 4, 5, 6, 6 elements. But since the indices start from 0, so n minus 1. This is the same loop. The external for loop is the same, but then I'm not going to run the internal for loop. That is how I'm going to save on the efficiency. And just by running one for loop, I would be getting the answer in the optimized approach by using something called the sliding window. So max sum and running sum, these are like, we can have it here as well, kind of global to the loop. So max sum is equal to 0 and running sum is also equal to 0. So let's start by incrementing. This running sum is going to getting incremented. Initially running sum is 0. So the first thing we need to do is to start having values or start populating the running sum. So that is how you increment sum counters. Running sum is equal to running sum plus nums. Let's call it, this array is called nums. So nums of I. Right. So in this case, the running sum will no longer be 0. It will go to something else. 0 plus 10 is 10. Right. And then what I'll do is I will basically do a check here. This kind of check. If so, what we are interested, the window size is 3, right? Let me write that as well. So all the subarrays has to be of size 3. So you can like imagine that what we are trying to do, we are trying to reach this thing, window size 3. So we can keep adding the sums until we have reached the window size, right? So sum will be initially, it was initially 0, then I added 10 to it, it will become 10. Then I will add the next element 0. So it still remains, sum remains 10. Then I will add the next element, that is minus 1, sum becomes 9. At this point of time, I have covered how many elements? I've covered 10. This element is covered. This was initial sum, right? I covered 10. Then I covered 0 because 10 plus 0 was 10. And then I covered minus 1. So this was the initial element. Then I covered 0 and then I covered minus 1. So when I covered these 3 elements, I have reached the window size. Window size is 3, right? I've reached the window size. So once you have reached the window size, it is a relevant sum now. because remember the max sum is basically comparing all the individual sums, and each of the individual sum is basically the sum of a subarray, and each subarray is supposed to be of size window size 3. So I've got my first subarray, and since I've got my first subarray, this sum that basically computes the sum of elements inside that subarray is a valid individual sum. So if that is a valid individual sum, it has to be compared with the max sum, right? So let's quickly code that out. So in this case, I'm going to write if the value of I, so if value of I is 0, right? So I think we can do this kind of thing. If I plus 1 is greater than equal to window size, right? If that is the case, we have to do something. Let me scroll down a bit. If that is the case, we can write something here. And that's it. So let's try to dry run the program, and then it will become all the more clear using only this much code snippet. So I'm starting with I is equal to 0, right? And then the sum becomes 10. This is covered. And then initial sum was 0. When I added 10 to it, I got the value of 10. Then this I keeps moving, right? 0 to n minus 1. So I was initially here. And then I came here. And when I came here, I'm adding the next value, which is 0 in this case. 10 plus 0, running sum becomes 0 again. So I'm calculating the running sum here. And I'm also keeping track of what is the value of I plus 1. So this condition is still not true. That is, so I will be not going inside this if loop. I keeps incrementing from 0, it became 1, and now it became 2. So now I came here. And now again, what is the value? Minus 1. So whatever is the running sum was 0. 0 minus 1 becomes 9. So this is how my running sum is getting updated every time by virtue of this line. And then if you examine this line of I plus 1, what is the value of I? 2. 2 plus 1 is 3. What is window size? 3. So 3 and 3 are equal. From this point onwards, I have hit the window size. This expression is become equal to 3. And from hereafter also, I plus 1 becomes 4, 5, and so on. It is always going to be greater than window size. At I is equal to 2, I have hit the window size. And from all next iterations of I, it is always going to be greater than the window size. So from this iteration, I is equal to 2 onwards, everything that is there inside the if loop is going to be executed. And now I think you can realize this, like I have got addition of 3 elements. So that is basically the window size 3. This is a running sum, which is now important to me. It is the sum of one of the possible subarrays. And then I have to basically get the max out of these possible subarrays. The max from the individual sums. That is what I want. So what I can do, I can quickly, and that is why we have kept the max sum. Initially, it will be 0. So the first max sum will be, since we are getting the first max, the max from the first possible subarray for the first time, this will of course be updated here. But from the next individual sum onwards, only if this condition is true, then the max sum will be updated. If the new max for the second subarray is greater than the previous max, then we are going to update it. Otherwise, we are going to keep it the same. So mat.max, whatever was the pre-existing value, compare that pre-existing value with the new max. So the new max for the current existing subarray is always given by the running sum. So whatever is the max, get the max and update it in the max sum. Now we have got this for I is equal to 2. We have got the value. Now we need to like move a little bit ahead, and now we are going to talk about I is equal to 3. But remember, we have to maintain the window size here. So what is the need of the R, right? We have got, let's say, this was the array, and window size was 3. So this, and this, these 3 elements we have got, and the window size is 8. Now what we need to do, we have to add this thing and we have to remove this thing, right? That is how we are going to move or slide the window. Instead of 0, 1, and 3, this is the next window. And how do I get the next window? By subtracting this thing, this is reduced, and you have to add this 4th element. That is how we are maintaining the window. So very simple. Think of this element addition. This is anyways getting added, right? Running sum plus nums is equal to I. So when the next, the for loop goes from 0, 1 to 3, ARR of 3 or nums of 3, this value that I'm supposed to add, this is already getting there once I start or begin the for loop. So nothing to do about it. The addition is taken care of automatically. But what about the reduction? So reduction, I have to reduce or remove this thing from the sum, ARR of 0, right? So that is what we do. Whenever we have inside this condition, we have to remove it. So how do we remove it from what? Remove it from the running sum. So I'm trying to reuse the previously calculated or previously computed sum, but just I cannot use it as it is. I have to modify it, right? I'm reusing it after slight modification. So the running sum, whatever was the running sum, addition is taking place here, running sum, and subtraction, I am doing it explicitly at this point of time. What I need to subtract, that is also important. So in this case, think of it. In this example, you have to remove from the sum ARR of 0 or nums of 0, right? So if I hard code it, like this will, just for understanding, you don't have to hard code it. You have to keep a generalized value here, right? So this is what we are doing. And then that's it. We have got the result. After the end of the operation, you can do a sys out. And what would be the answer? Max sum would be the answer, because by that time max sum would have computed all possible running sums, which is basically the sum of all possible subarrays. Out of all those subarrays of window size 3, what subarray has the maximum sum? That is the answer stored in maxsum, and we can simply print it out. But you have to generalize it, right? Think of this loop. This window is continuously moving forward, right? So if this window moves like this, 2, 3, 4. So next time it has to subtract or reduce this thing, 1 from the previous calculated sum. Next time the window will move from 3 to 5. 5 is added in the forward direction and 2 is reduced. So it's not that 0 is going to be indexed always at this point of time. So if we can analyze the pattern, then we can simply plug in the generalized value. So when I is equal to 2, I'm getting the value 0. So how did I get 0 here? So basically you can see I plus 1, 2 plus 1 is 3 minus window size. This is the generalized expression. Right. So next time when I is equal to 3, 3 plus 1 is 4. 4 minus window size is 3, right? So 4 minus 3 is 1. So initially 0 got eliminated in the backward direction, and then 1 got eliminated, and so on. This is the general expression we would be needing to plug in here, not 0, but this expression. And that's it. So in the backward direction, we have to reduce one element. This is taking care of reduction. And this is taking care of addition of one more element. And that's it. Just by using one for loop, we are able to achieve the answer. So that's it. The understanding of the problem as well as the programmatic approach. And that's it. I think you have the answer right before you, but if you want, this is the answer. Same approach. We have got the nums array. The data has changed, but the approach is same. So if you examine this array, I think window size is 3. So all possible subarrays, we have to first calculate all such possible subarrays. Out of those all possible subarrays, each subarray will give an individual sum and get the max from those individual sums. So in this case, 70 is the max possible sum, which is got by adding these 3 elements, 20, 30, and 20, right? 70. These 3 elements, this is the subarray, which is giving the sum 70, and it is the maximum possible. No other subarray can exceed this sum 70. How do we got it? Same approach. Maxsum is equal to 0, running max is equal to 0, window size is 3. That is given to us, window size. The initial array and the window size is given to us. Then we are running one loop, I is equal to 0 till the very length of the last index. The last index of any array is always length minus 1. So my I is less than the length. So this loop is basically running from 0 to n minus 1 indices. Or here you can say length minus 1 directly index, right? Basically traversing the whole array. And then we are like calculating the running max by repeatedly adding whatever was the pre-existing running max, adding nums of I to it. And if this is the condition, we are checking have we met the window size, right? This is the question I'm asking. In this case, window size is 3. So in this case, like 3 is the answer. So once I've met this condition, I have met the window size, and thereafter we maintain the window size. That is why it is important to have not just equal to. That will be a wrong approach. That is a common typical mistake. Some students who memorize it make a mistake out of it. So no memorization. We should be always maintaining the window size, right? We have to examine all possible individual sums of window size 3. And out of all possible individual sums or subarrays of window size 3, we have to get the grand max. So, right, and this is basically comparison among the individual maxes, or you can see the subarray maxes. Right, and this is basically the grand max. The max among all individual subarray maxes, where each subarray is of length equal to window size. So we have to examine all subarrays, but not just any random subarrays. The length of the subarrays whose length is equal to window size. Among those subarrays, get the max, and among those max, get the grand max. So after doing this, then we have to maintain the window. Now this is basically maintenance of the window, and maintain the window by virtue of adding new element at end of window and removing first element at starting of window. 2 operations, right? 1 element each. So this operation, wherever it is, okay, we have not done it, so let's do it. Nothing's IntelliJ is automatically like adding some points. So here we can do is inside the loop, right? We have to do it inside the loop. So here I'm already doing it. This is the thing, right? This is nothing but adding to beginning of window. Or it should be to end of the window. My bad, adding 1 element at end of window. This takes care of the addition operation, and this is basically removing one element from end of the window, so as to maintain. So you're removing element from the end of the window so as to maintain this thing. Right, so pretty simple. We are almost at the end of it, and then once this whole for loop I is equal to 0 to length minus 1 index, this traversal is complete. By this time, we would have examined all the individual sums, and from all those individual sums, we would have got the grand max, which is stored in the value max sum, maximum among all possible running maxes, and that would be the answer, right? So let's try to run this program, and let's see what output it generates. I've already run it once, so let's quickly run it again. 70 is what the output is, and 70 is indeed the max which we have got from this subarray 10, 20, 30, and 20. If you add them up, windowSize 3 is 70. Any other possible subarray would not give a max greater than 70. So 70 is indeed the answer. So this is how you use the sliding window mechanism. At the heart or at the core of this algorithm or the pattern is nothing but keeping track of this. So initially this is windowSize 3, then you slide it like this, then you slide it like this, and then you slide it like this. And whenever you are sliding, you are getting some value out of this possible, out of this possible, out of this possible, out of this possible. These are basically the individual maxes. All those individual maxes are the max got from a subarray. Compare every them and get the grand max. And you already know how we have moved from brute force approach to the optimized approach. And in the optimized approach, we are not running 2 for loops. We are just running 1 for loop and getting the answer, which has a better runtime complexity than the brute force approach. Pretty simple. We just need to go through it and the concept will sink in. This concept has applicability in other problems as well. The mechanism of sliding the window and using just 1 for loop to keep track of the counter of a fixed window length. That is the approach. So if you like the video, please do subscribe to our channel. You can visit zboard.com for all the details. Contact us at these numbers, and we can also be contacted at contact@zboard.com. For getting continuous updates, please do like and subscribe our channel so that I get motivated, and as an organization, we can keep adding more fruitful videos. Any suggestions are most welcome in the comment section. Thanks guys for watching, and I hope you have a nice day. Thank you.